dark adapted, and hence the scotopic vision is in full action. Another measurable difference in retinal sensitivity for scotopic and photopic vision is the change in sensitivity across the retina itself. Figure 5 shows a curve representing the variation in sensitivity across the retina for photopic vision. The foveal region shows a maximum sensitivity with a smooth decrease towards the periphery. The blind spot corresponds to the point of entry of the optic nerve in the retina, where there are naturally no receptor elements. In Figure 6, a similar curve is shown, but this time for the scotopic eye. It will be seen that the fovea shows the lowest sensitivity under low levels of illumination, and this is supposed to be due to the absence of rods in this region of the retina. It is interesting to observe that the curve in Figure 5 follows rather closely the cone distribution across the retina. Adaptation. We have had occasion to use the term adaptation before defining it. It will not be necessary for our purposes to present the mass action principles involved in the adaptation process, but suffice it to state that the eye becomes adapted to various light intensity levels after certain periods of time, chiefly because of an equilibrium that is established between the formation and destruction of the retinal visual purple, and because of the involuntary changes in the opening of the iris. The latter factor can account for a small amount of the total adaptation only, although in photographic literature one is often led to believe that the iris is the only factor in operation. When one speaks of the fully dark adapted eye, reference is made to scotopic or rod vision, while the expression daylight adapted eye refers to the photopic or cone vision. Visual acuity. The ability of the eye to distinguish fine detail is chiefly dependent upon the perfectness of the lens system and upon the limits of resolution imposed by the structure of the recipient elements of the retina. Actually, the seek of distinct vision is limited to a very narrow angle, 1 degree, corresponding to the coverage of the fovea. As we have seen, the cones in the fovea are closely packed, and each cone has a direct nerve fiber leading to the optic nerve. By reflexive action, the eye focuses its image upon the fovea, not upon the optical axis as might be expected. Outside the bounds of the foveal image, the sharpness of vision is greatly reduced, as can be seen from the diagram in Figure 7. The measurement of visual acuity is no easy job. The test procedure has to be carefully planned and many factors properly considered in evaluating final results. Visual acuity varies widely in different individuals, and results obtained with any given individual are greatly dependent upon adaptation, type of test object, glare, nature of surroundings of test object, etc. But one outstanding fact is that the visual acuity and the ability to distinguish variations in intensities are closely related. A black object on a white surface is readily distinguishable, but as the background is made more and more gray, the discrimination becomes increasingly difficult. In testing for the minimum perceptible contrast, large areas are employed, one of which is varied in intensity so that the barely perceptible brilliance difference is established for different adaptation levels. Typical results are shown in Figure 8, which LA is the adaptation luminosity and LB is the luminosity of the outside ring of the test object, and LO is the luminosity of the center disk of the test object. From these data, it is evident that contrast discrimination increases with luminosity. Thus, we can expect that visual acuity will vary with adaptation level and have a maximum at high values. The work of Lithgow, as well as others, shows this to be true. In Figure 9, a curve gives the increase of acuity with luminosity. For this work, Lithgow used the international test object shown in Figure 10. which is a broken circle having an opening equal to 1/5 of the outside diameter of the circle. By orienting the test object at different angles and asking an observer to judge the position of the opening, a measure of acuity is obtainable. It is interesting to note that the results vary according to the color of light being used. Sodium vapor, yellow for example, gives higher values than incandescent lamplight. With red light, visual acuity is worse than for white, and for blue it is very poor. For a complete study of visual acuity, see the bibliography at the end of this article. Resolving power of the eye. More commonly used in photographic circles than visual acuity is the resolving power of the eye. This property of the eye is distinguished from acuity in that it is a measure of the eye's ability to distinguish fine detail when there is a large contrast between object and background, whereas acuity involves small brightness differences of extended surfaces. It is generally assumed in photography that the resolving power of the eye is a rather fixed property equal to 100 lines per inch. We shall see that the value is much higher in many cases and certainly not a fixed property. When viewing an object, a very much reduced image is formed upon the retina. How much detail the eye can discern will depend largely upon viewing distance and the size of the original. Using as a basis the concept that the eye can resolve two lines or dots which are separated by 1 minute of arc, objects to be recognizable cannot be placed farther away than 3,440 times their longest linear dimension. At this distance, no detail in the subject can be registered, but the subject itself can be distinguished from other objects. The question is, what is there about the makeup of the eye that limits the resolution to this relatively low value? It would simplify the explanation if we had to consider only the limiting factors of the retina. However, the problem is considerably more complex since resolving power is influenced by imperfections of imagery, type of test objects, illumination conditions, retinal limitations, quality of light source, and other factors. For present purposes, we need not consider all these factors. We know that a point of light is never focused upon a focal plane as a true point, but rather it is focused in the plane with the light spreading outward from a bright central image. The distribution of the light in a typical case is represented by the curve in Figure 11. If 2 points of light close together in the subject form distribution patterns of this type on the retina, the overlap of the border intensities tends to cause the points to visually merge together. The 2 points can be distinguished provided there is a difference of 10% in the intensities at points A and B. The effective distribution of light is shown in Figure 12. Along similar lines of reasoning, it can be shown why it is possible to see a much finer single black line on a white background than it is to distinguish between two black lines separated by a space equal to the width of the lines. This will also clear up the apparent fallacy between the least perceptible image and the least separable image. It has been shown that the eye can easily see a small wire against a bright sky in which the angle subtended is but about 4 seconds of arc, while the resolution of a series of parallel lines under best conditions never approaches this low limit. The explanation for this is seen in Figures 13 and 14. The dotted lines in Figure 13 represents the overlapping light distributions from the white borders surrounding the black line. The effective light distribution on the retina is shown by a solid line. Thus, a black line of 0.5 Greek me, so it's probably 0.005 width is perceptible, since the difference in brightness is about 10%. Now in the case where two black lines are separated by a white space, the situation is considerably changed. In Figure 14, the white center line forms a distribution pattern that overlaps with the borders of the distribution curves of the outer white surroundings. The final light distribution follows the solid line. Here we have two black lines of 2μ separated by a 2μ white space, resulting in a retinal image that is not perceived as two lines, but as one. In this case, the variation in intensity between the central white space and the adjacent black lines is less than 10%, clearly showing that 2μ separated lines are not as effective as a single 0.5μ line. In the above cases, ideal subjects of maximum contrast have been considered. However, as shown conclusively by Cobb and Moss, visual acuity is depreciated when the contrast is lower. We have already seen how acuity is affected by luminosity, but actually it is a function of both luminosity and contrast. For example, had the subject in Figure 13 been a light gray line on a white background, we would find that in order to perceive it, the width of the line would have to be considerably wider. With a gray having a reflection factor of 0.5, the line would have to be about 1μ. Accommodation. One of the surprising functions of the eye is its ability to adjust its focus according to the distance of the subject viewed. This action is accomplished primarily by changes in the curvature of the crystalline lens, but the ability to do this varies widely in individuals and is progressively lost in all individuals with age. Ability to accommodate the focus is largely a matter of training and practice also. Some optometrists are treating patients by exercises designed to improve accommodation without the use of glasses. Certain investigations point to the fact that accommodation is mostly a matter of mental interpretation of the retinal image. It is thought in some ways that optical aids destroy the will to see, making the use of mental accommodation sluggish. As a result, we have such things as progressive myopia, in which persons afflicted with minor malfocus of images, although getting relief by corrective spectacles, find that periodic changes in correction are required. The problem of accommodation is far from thoroughly explained. It is an interesting study, but one which does not have considerable bearing on the discussion here. Binocular cooperation. In the normal person, both eyes form retinal images which are blended together in the brain to produce a single impression. Each eye gives the observer a different view. It is this fact that accounts mostly for our binocular depth perception. The movement of the two eyes in perfect unison is the result of persistent practice and is completely automatic. When the eyes become fatigued, however, the binocular cooperation is affected and one experiences double images. The movements of the eyes are simultaneous in two distinct senses. They move in unison when scanning an object at a given fixation distance, and the angle of view of each eye changes for different points of focus. The latter is referred to as convergence. Visual mechanism in relation to pictorial photography. No effort has been made in the foregoing description to present a comprehensive discussion on the visual mechanism. Actually, even at the risk of superficiality, the treatment has been made brief, since only by reference to original papers and standard texts can a thorough understanding of the many problems and complexities involved be achieved. Sufficient references are given at the end of this article for those who wish to pursue the study further. However, it is hoped that this meager insight into the operation of the visual mechanism will provoke a more intelligent outlook in any consideration of a visual and photographic correspondence. It is at least clear that the visual process is not a simple one. The eye has developed in man by many evolutionary steps. Just how and why the present stage of development has been reached cannot be stated, but it is certain that other arrangements have different visual properties could have been possible. In the present stage of development, an imperfect optical image is produced upon a complex layer of cells which are stimulated by photochemical reactions. The nerve excitations are registered in the brain by completely unknown processes, although it is known that the mental state of the observer, his memory,
the mental perception
and numerous
of the scene
psychological
not
factors
necessarily,
enter into the
perhaps
final
never, correspond with the dimensional proportions of objects as projected upon the retina by the optics of the eye. For example, a 6-foot man 20 feet from an observer will form an image about 0.3 inches high on the observer's retina, assuming the focal length of the eye to be 1 inch. A camera with a 1-inch lens will also form an image of 0.3 inch high. Another 6-foot man at 100 feet distance will be imagined by the eye and the camera, only 0.06 inch in height. This shows a perfect correlation between the two optically formed images. As pointed out by Thoulis, however, what the observer sees, that is, his perception, will be two men not nearly so different in size as indicated by the linear differences of the retinal images. Accordingly, lest photographers continue to place too much emphasis upon an ill-established criterion, it seems desirable and timely to examine the nature of the visual mechanism. A knowledge of some of the characteristics of the eye, both structurally and functionally, will do much to lessen the dogma that has been built up around the photographic visual correspondence. It will also make possible appreciation of certain fundamental limitations in this supposed idealistic correspondence. The structure of the human eye, evolutionary development. The human eye is one of the most complex structures of the body. It is developed through a long series of evolutionary processes, and like other complex body organs, it is only through a tracing of the major levels of development that one is able to perceive how such a specialized mechanism could evolve. To begin with, all protoplasmic substance is light sensitive to some extent. In the lower unicellular organisms, the response to light can be observed even though an organ of vision is absent. In the multicellular animals, groups of cells become specialized in their response to light. For example, in the lowly Aurelia, common jellyfish, there are localized pigmented surface areas packed with nerve cells. The pigment acts as an efficient light absorber and is an accessory organ to the nervous tissue. In the higher evolution of the eye, one finds that the sensitive areas and accessory organs are equally important, both very specialized and structurally rather independent, but functionally cooperated to the highest degree. Various steps in the development of the eye are shown in Figure 1. These examples have been compiled from various references, but any number of similar sets could be chosen to show the same evolutionary development. Interesting to note is a marked parallel between the development of the human eye and the eye of the higher mollusks, the cephalopoda. In the eye of the nautilus, for example, a fluid is found in the eye cavity. The next stage is the formation of the lens. And finally, in the octopus and cuttlefish, the cephalopod, eye finds its highest level, not far removed from the human eye. The human eye. In Figure 2 is a detailed drawing of the human eye. Each part will be discussed separately, but completeness of description will depend upon functional importance from a photographic standpoint. A great part of the eyeball is covered by 3 successive layers: the sclera, the choroid, and the retina. The sclera is a tough, thick, protective outer layer. The choroid is a centrovascular membrane, thin and dark, to function somewhat as the non-halation back coating on a photographic film. The retina is the inner layer covering the entire posterior chamber of the eye, consisting of a complex nerve structure along with special sensitive elements. At the anterior bodies of the eyeball, the sclera merges with the equally tough but clear cornea. The cornea is so transparent it is hard to see, but upon careful examination it is observed to be a convex layer, which is the first refracting surface in the optic system of the eye. The choroid layer not only acts as a light absorber to prevent scatter, but it also provides nutritional elements to the eye through its highly developed vascular system through which blood circulates. The choroid thickens near the front of the eye and, in ring fashion, extends completely around the cornea. This ring is a ciliary structure, and because of its radial muscular makeup, performs the very sensitive and specialized task of accommodation. The ciliary body cannot be seen when looking into the front of the eye because of the further continuation of the choroid, which passes over in front of the lens of the eye. This extension of the choroid is known as the iris and is the colored ring as seen from the front of the eye. It is equipped with independent muscles to automatically produce contraction and dilation through a range from 2 to 6 millimeters when the external light intensity is varied. Although the inner layer of the eyeball, the retina, is next in order for discussion, its description is best left until a few comments are made in regard to the optical system of the eye. Behind the cornea and iris is a chamber filled with a transparent fluid called the aqueous humor. Separating the aqueous humor from the inner chamber of the eyeball is the crystalline lens, double convex. The crystalline lens is located immediately behind the iris and is supported in a capsule to which are attached connective ligaments going to the ciliary body. It is this mechanism that controls the shape of the elastic lens. Behind the crystalline lens is located the inner chamber filled with a thick non-liquid vitreous humor. The cornea, aqueous and vitreous humors, and the crystalline lens all contribute to the dioptric system of the eye. Their respective descriptions as presented here should not lead one to believe that they are homogeneous structures, for it is known that the crystalline lens consists of laminae, like layers on an onion, and is fibrous. There is also reason to believe that the vitreous humor is supported by a crisscross mesh. These facts add to our understanding of certain diffraction characteristics of the eye. The axial length of the human eye, from the anterior corneal surface to the retina, varies from about 20 millimeters to 36 millimeters in different individuals. In the normal eye, the average length is about 24 millimeters. The radius of a curvature of the anterior surface of the cornea is from 7 to 8 millimeters, while the posterior surface is usually less than 7 millimeters. The thickness of the cornea is about 0.5 millimeters, and its refractive index is approximately 1.376. The axial thickness of the aqueous humor is roughly about 3 millimeters, and the index of refraction is 1.336. The thickness of the crystalline lens is about 3.6 millimeters and remains constant even during accommodation. The anterior radius of curvature of a relaxed eye is about 10 millimeters, and that of the posterior surface 6 millimeters. Actually, it is impossible to assign a single index of refraction to the crystalline lens, since each layer has a different value. At the vertex is found the lowest value, around 1.388 at the center, a maximum value of about 1.411. Sometimes a total index is assigned, which is the index of an optically equivalent homogeneous lens. This value is calculated to be 1.42. The total refracting power of the human eye when totally relaxed is of the order of 59 diopters. The diopter of a lens is the reciprocal of its focal length expressed in meters. This is often called the power or strength of a lens. Do you want me to read the retina?
Okay, that's good enough.
Okay. And I can read you the retina and then the visual path
Okay.
later.